Hello, everybody, and welcome. So I am Ron, and I'm going to switch over from this video to my slides so we can do a few introductions and get into some awesome computer video. All right. So welcome to Putting Eyes on the IoT. It's all about computer vision using the Go programming language and OpenCV 3. So welcome. I'm Ron Evans, aka Dead Program on the internet. I'm on Twitter, Facebook, GitHub, all the important places. I'm Dead Program. I'm not dead, not yet, but I am Dead Program. And I'm the ringleader of the Hybrid Group. So the Hybrid Group, we are a software development consultancy that specializes in doing the software for hardware companies. Some of our clients that we've done include Intel. Thank you very much, Intel, for inviting me today. A company called Sphero that's done a lot of robotics work for some movies that have come out about wars in the stars. That's about all I'm allowed to say. And we've got some really amazing partners. In particular, I want to say a special thank you to my colleagues at Momentous, which is where I'm doing this live broadcast from today here in northern Spain. Momentous, amazing company, and we're doing some really exciting things together. So Hybrid Group, we've got some open source projects that we've become pretty well known for. And the best known of them is GoBot, which lets you do Internet of Things, robotics, and drone development all in the Go programming language. And during the first IoT DevFest, that was my talk, and you can go back and check out the video about that. There's lots of information available at gobot.io. But move over, GoBot. There's a new gopher in town, GoCV. So GoCV, which you can check it out at gocv.io, is our latest project. It's only been around for just over 1 month, and it lets you use OpenCV 3. OpenCV is the leading computer vision software. It's got literally hundreds of computer vision algorithms, and it lets you use OpenCV 3 from the Go programming language. So how cool is that? It also supports the Intel Computer Vision SDK. So the Intel Computer Vision SDK is sort of like OpenCV with superpowers. It takes OpenCV and then adds to it some special secret sauce algorithms from some of the Intel super geniuses. And it also adds hardware acceleration, so you can take advantage of some of the special hardware that you've got in there. So we'll get into a little bit more about that later. So first of all, some definitions. What is computer vision exactly? So computer vision is when we give a computer the ability to process visual data in a way that we would normally only associate with human abilities and capabilities. So what can you actually do with computer vision? For example, we can detect motion and track objects as they move around. We can recognize people, and we can determine their sentiments and emotions based on their facial expressions. We can do telepresence, whether that is telepresence for medical telepresence, checking up on people who are homebound or hospital visits, as well as telepresence on other planets, such as Mars. And autonomous vehicles, trains, planes, and automobiles, as well as, the epiphany drones, and then augmented humans, whether that means providing additional support for people who are visual impaired or giving new capabilities for people so that we can see into spectrums where we are not able to normally, or process visual data for measuring crowd size or other things which are very, very difficult for humans to do. So why you should use the Go programming language for computer vision? Well, quite simply, you should be using Go for everything. Go is a very, very powerful language. It's a simple language, but very, very powerful. First of all, Go's concurrency. Concurrency is doing more than one thing at the same time. And the programming model that's used by the Go programming language is one that's called the CSP, for Communicating Sequential Processes model. It's a very simple way to be able to obtain concurrency. And Go, by default, uses all of the cores on your multi-core machine. So without doing anything special, if you're using just the basic Go concurrency primitives, you're able to use all of your cores and get the maximum performance out of whatever hardware that you happen to be using. So portability, Go has got an excellent cross-compiler tool chain, and Go code will normally operate on every platform that it supports. And in the case of GoCV, there's a few little tricks to us being able to achieve that, which I'll talk about in a minute. And then performance. So Go is a compiled language. It is statically typed or strongly typed rather, and statically linked. So you're able to get the same kinds of performance out of Go that we associate with other compiled languages. And I was just recently in Paris speaking at the amazing .go conference. And one of the talks was from a researcher that does bioinformatics and genetics research. And their team had tried to substantially improve the processing time for doing gene sequencing, which involves very large amounts of data. They did it in Python, they did it in Java, they did it in C++, and they did it in Go. And Go was the most performant. So that's very interesting. So how GoCV works is it takes advantage of one of the capabilities that the Go programming language has, of being able to call the C programming language right from within Go by using something that's called CGO. And CGO actually compiles the C code right into the same executable along with your compiled Go code. So it's just a single file. In the case of OpenCV, all of OpenCV's code is developed in C++. So we've written C wrappers around the C++. So it's Go to CGO to C to C++. That sounds kind of complicated, but we've done a lot of work to make it so that you as a Go programmer have a very easy and nice Go language experience, and most of this complexity is hidden for you. And the big benefit is that it works on Linux, it works just as well on OS X, and it runs on Windows. Yes, I said Windows, that's right, we support Windows. Many open source projects don't really give enough support to the Windows community, but recently, the most recent statistic I heard was 86% of desktop computers are still running Windows. So it's very important that we pay attention to that community and we help Windows developers get a lot out of these tools. So let's take a look at Hello World in Go. If you have not done any Go programming, this is for you. So here is Hello World in Go. So first we say package main. This is the equivalent of your main program in your C program. And then we say import, which brings in an external part of Go, which is actually part of the Go standard library. It's called FMT, or as we pronounce it, FMT. And then we have our main function, again, very similar to a C program. And our main function says FMT println hello world. So it's just a very simple hello world. So let's go over here and here's the font here for you. So let's say go run demo hello world main.go. So that compiles and runs the code, and we get the output hello world. All right, good place to start. So now let's take a look at the hello world of video. So the hello world of video looks very similar to the hello world program. We still have a package main. In this case, though, what we're importing is the GoCV package. And this is where all of the GoCV code is located that we're going to call. Then again, we have a function main. And so our function main, first we create a webcam by saying GoCV.video capture device. So this creates a new video capture device and associated it with the camera number 0. Then we create a new window, and we say GoCV.new window, hello. So this is going to create a window for us to put the video in so we can see it. And then third, we create a new image, and we say that's equal to GoCV.new mat, a new image matrix. I'll explain what that is in just 1 minute. So in Go, we say for, and that means basically just repeat infinitely over and over. And so we say webcam.read, so that reads from the webcam and puts it into the image. Then we say window.imShow, and so that's going to show the image in that window. And then we say GoCV.waitKey1, which says wait for 1 millisecond and then repeat. So if we go to our demo, and this time we say go run demo hello video main.go. So I'm going to run hello video. And if the demo gods are kind, it will compile the Go code. It takes a bit longer this time because it's also compiling all of the C and C++ code that we need to communicate with OpenCV. And then there we see a much better camera view. Hello. Yeah, the lighting is a little better this way. I have an excellent computer. It's a Dell developer XPS 13, but the camera angle is a little odd since it doesn't have any bezel on the screen. Anyway, so there's hello video in Go. All right. So what about the mat? So the mat is a matrix, and the matrix in OpenCV is a very, very important concept. It's basically something that has a number of dimensions, often 2-dimensional, and a number of channels, often 3 channels corresponding to the blue, green, and red of your RGB type of image. So it's usually pretty much always used to represent an image. However, in OpenCV, a mat can also be a list of things, or it can be a vector of things. It's a multi-purpose data structure that's used by OpenCV for all sorts of different purposes. So it's really, really useful. So now let's talk about tracking faces. This is sort of the canonical application of computer video is tracking people's faces. And so the way that we're going to do it is using something called a Cascade Classifier. So a Cascade Classifier is a very efficient way to try to take and locate an image, a part of an image that corresponds to something it's been trained to know about. The reason why it's efficient is it takes and it subdivides the image into different pieces, gradually refining, looking for the features that it knows how to recognize. If it doesn't see the features at a higher resolution, or a lower resolution rather, there's no reason to look for the higher resolution features. So it's very, very efficient. So in OpenCV and then GoCV, again, here's our program. We have a package main. We're importing the font package again. We're importing the image color package, which is part of the Go standard library. And then we're importing GoCV itself. So our function main, same as what we had before. First, we're using device ID 1 because that's actually the device ID of my second camera, which is a Creative Labs live cam, very common webcam that you can get. So we're going to open the webcam. We're going to open the webcam by calling the same function video capture device. This time we're also looking to see if there's an error coming back. And if something goes wrong, if the error is not equal to nil, then we print that error and we return, which means exiting the program. Otherwise, we defer webcam.close. So defer, again, is a very, very powerful part of Go. It allows us to say, whenever we're actually done with the webcam, close it. That way we don't have to worry about closing up resources when we're finished with them. They just automatically get cleaned up for us by Go. It's very, very nice. So then we open the display window, same as before, again, deferring the close of that. We prepare our image matrix that we're going to put these images in. And then we declare that the color blue is equal to color.rgba, which is part of the Go standard library, for the color blue. So now here we're going to load the classifier. We're going to say classifier equals GoCV.new Cascade Classifier, and we're going to load that with a data file that contains the training set for people's front of faces, something that is called a HAR cascade file. So it's been trained using the kind of filters. And then we're going to repeat infinitely. We're going to read from the webcam into the image. If the image is empty, we're just going to loop through again. There's nothing to update yet. Otherwise, we're going to ask the classifier to classifier.detect multiscale from the image. That means if there is more than one face, it will detect however many it's able to, and then it puts them into this rex variable. So that will contain a slice of image.rectangles. In the Go programming language, a slice is like an array, but it's an array that can change its size, so we don't have to declare a specific size up front. So this will contain however many recs there are. And so we're going to say for r equals range recs, which goes through and iterates through however many recs there are, if any. If there are any, then it's going to GoCV.rectangle, which is part of GoCV's wrapper around OpenCV, which will draw a rectangle on our image at that rectangle position in the blue color of thickness 3. So then we show the image, and then we wait for 1 millisecond and loop through again. So let's take a look at that. A little bit of code, but it's worth it. So I've taken the liberty of compiling this code so that we don't have to wait for it, since time is of the essence. And so here I am. And it looks like it's recognizing something on the wall behind me. That's kind of a square face looking, looks vaguely face-like. That's kind of scary. Is that like a poltergeist coming out of the wall, or I don't know. Anyway, so it's tracking my face and it's drawing the square box around it like we saw in the code. All right. If there's a face in the wall behind you, run, I guess. I don't know. All right, so now let's talk a little bit about the Intel Computer Vision SDK. So the Intel Computer Vision SDK, as I mentioned, it's sort of like OpenCV, but with extra superpowers. And the one that we're going to be taking a look at is something called the Photography Vision Library, or the PVL. So the PVL, basically, it allows you to do some more sophisticated analysis of things like faces. You can do sentiment analysis. You can do facial recognition, not just facial tracking. But we're going to use it to do something that I like to call the smile detector. So the smile detector, we've got a package main. We've got a few of our Go standard packages. We've got GoCV, and then we've also got the GoCV PVL subpackage. So this allows us to use the special capabilities of PVL, but also be able to use the same GoCV wrapper around, just regular OpenCV without the extra abilities. So our function main. First, we make sure that all of our arguments are in place because we pass in which device ID it is in case I'm using a different camera. So then we open our webcam, same as before. We open our display window, same as before. But this time, we're going to actually create a couple different image matrices. We've got one mat, which is for the image coming in from the camera. And then we've got a second mat, which is going to be used for a converted grayscale version, since that's actually what the PVL prefers for doing the facial detection. So then we've got two colors that we're defining, blue and green. And then we load the PVL face detector. You'll notice that we don't need to load a HAR cascade file or any training file because the PVL face detector has its own internal representation based on its own training. But we do say face detector dot set tracking mode enabled equal to true. In the PBL's implementation of face detector, it's able to say, if I'm already tracking a face, if I've already detected the face, you don't have to keep detecting it over and over. You can just track where it is moved to. That way, we can be more efficient about our use of tracking resources if we're tracking multiple faces. So then we're going to start our for loop. We read our image from the webcam into the image mat. If it's empty, we loop through, same as before. So here we're going to GoCV.convertColor, and we're going to convert the image mat to image gray using the color BGR to gray conversion, so converting it to grayscale. And then we're going to use the face detector, detect face rect from the image grayscale mat. And then we'll put that into the same as what we did in the hard cascade. It puts it into a slice of Go image rectangles. That way we can do something with it. So in this case, we're going to range through these faces since each one corresponds to a face. And then we're going to say face detector, detect eye. So detect eye looks at the smaller section. Remember how a Cascade Classifier can look at subsections? So this just runs a classifier, again, inside the face detector, the PBL face detector, to detect where the eyes are. And then it does the same thing to detect if there's a smile or not. If there is a smile, it uses the green color, otherwise it's blue. We get the face rect. We draw that rectangle in whichever color it is, and then we'll display some text to say human over it. We just keep looping through that for however many faces there are. Then we show that image in the window and wait. So let's go over here to run this smile detector. And I am a human, and I'm a happy human. It's actually working, yeah! I know, it's really, really neat thing to be able to do, because that way, if you have retail applications where you're trying to sort of analyze the general sentiment of the people as they're shuffling through your retail location or other places, you know, it's a nice thing. All right, and it's something that is a unique capability of the Intel photographic vision library. So let's talk about the 3 most common searches for OpenCV, how to do. So I went on my Google search engine. I usually use DuckDuckGo, but I went on Google because of Google Autosuggest, and I took a look to see what the top searches were for OpenCV how to do. Once you got past the, OpenCV how to install, which we've already addressed with our installation instructions for the Linux OS X and Windows. You basically discovered that were 3 common applications that people typically want to do with OpenCV and, consequently with computer vision. So the first one is motion detection or tracking. So we want to track objects or as they move around or detect motion in some form. The second one is MJPEG streaming. We want to be able to stream to the internet from our OpenCV setup. And then the third one is object counting. We want to be able to count things, how many of them there are. So let's get into the first one, motion detection and tracking. So to do motion detection and tracking, one of the best ways to do it is to be able to separate the background from the foreground. And we do that in OpenCV. In this particular example I'm about to show you, by using a method that's known as the mixture of Gaussians. So just as a quick refresher for everyone who fell asleep in math class or statistics, so a Gaussian is sort of like an average. It sort of blends out and puts it into this classic sort of bell curvy shape. So by taking a mixture of Gaussians, we're able to extract what the difference is between a non-moving background and a moving foreground. So let's take a look at some of the code. So again, package main, we're importing our usual suspects from the Go standard library and GoCV. So then we have a constant here of saying minimum area equals 3,000. So that's going to be a measurement we're going to look at to decide if something is actually moving or is just some artifact of our camera. We parse our input to get the camera ID. We open up our video capture device, same as before. We open up a new video window, same as before. This time I'm going to say window.setWindowProperty full screen, just that way it automatically goes to full screen. So then we're going to create 3 mats. We've got an image mat from the camera. We've got an image delta, which is the one we're going to use to extract the foreground data, and then image threshold, which is a mat that we're going to use for doing some cleanup of the image before we do image processing. So then we've got our new background subtractor MOG2. So we're using the mixture of Gaussian 2 algorithm, which is an adapted version. And so this algorithm is what we're going to use to apply to the images to determine whether or not it's the background or foreground. So then, same as before, we start reading the image from the camera. If it's empty, we continue. We set our status message and our status color, and then we begin the first phase of what we're going to do here. We use MOG2 algorithm and we apply it using the image as a source and the image delta as the destination. So this is saying apply the background algorithm, apply the MOG2 algorithm, and put the result in image delta. So then the second thing we're going to do is called the GoCV.threshold function. And this is going to do some cleanup, taking it from the image delta and putting it into the image threshold, cleaning it up using basically helping us get rid of any noise or extra artifacts. And then we're going to call the GoCV.dilate function, doing the same thing again, just to get rid of any extra little speckles or noise that might happen to be around. Then we're going to call the GoCV.findContours function. So findContours is going to take this cleaned up image mat and it's going to find the outlines around anything that still exists, anything that's going to actually be moving. So it's going to loop through the range of contours, get the contour area, make sure that it's at least our minimum, which if you recall from up here is at least 3,000. And then if it's not the minimum, just loop through, it's too small to worry about. Otherwise, we're going to get the rectangle for it and draw that on the screen, in red. We have detected something and here's where it is. And then, so then we're going to show our status message and loop through again. So let's run that code. But first, before we do that, I'm going to turn around my camera so it's facing the other way. And I'm going to, let's run the code. All right, so there's the desktop of my desk here. And so let's see if it's able to detect any motion. Oh, hello. Who are you? So as you see, when there's nothing on the screen, it says ready up at the top left-hand corner there of the image. And then when whoops. Uh-oh. Where's my robot? Trying to hide. So then when the robot comes onto the screen, then it's able to detect the fact that there's motion. All right, you can go away now. And let's go and exit that program. All right, well, that was kind of fun. All right, so let's go to now our next application, typical application, MJPEG Streaming. So MJPEG, if you are not familiar with it, is short for motion JPEG, and it is a accepted standard for basically just taking a series of JPEG images and then putting them in a series so that you can stream them. So it's a really, really nice way to be able to display things in web browsers where it's already basically always supported. So if you take a look around, you'll see people are doing all sorts of crazy hacky ways to try to get some video and feed it into one of the existing command line tools. But you don't have to do that in Go. You can do it all in just pure Go code with GoCV. So let's take a look at, first we start with package main, and we've got our import here. We've got our usual suspects from the standard library. We've also, now we're importing another package. It's the SalJam MJPEG package. So the MJPEG package knows how to plug into the Go standard library's web server and do motion JPEG streaming. So we'll be able to plug into it really easy from GoCV. So we declare a few variables here, our device ID, our video capture webcam, our image matrix, and then the stream for our MJPEG stream that we're going to use. And here we have a separate function that we're going to use for capture now. And this function basically is doing the same thing that we've seen before, but just extracted into a separate function for readability. So we grab the image from the webcam. If it's empty, we continue. If it's not, and we have the image, then we call the GoCV.ImEncode function. So ImEncode takes any given image mat and converts it to whatever format you want. So we say convert it to a JPEG and then put it into this buffer. And then we tell our motion JPEG stream to update the current JPEG using that buffer. So that's it. So then our main function, we parse our arguments, we open our webcam, we prepare our image matrix, then we also prepare our mjpeg.newStream, so that initializes the stream that we're going to use up here. And then we call GoCapture. So GoCapture, whenever we use the Go keyword in the Go programming language, that says run the next code asynchronously. So it starts up what's known as Go routine, and it just runs this capture routine in a separate green thread, so it's completely concurrent. Then we start our HTTP server. We use the Go standard library's HTTP package, and we say handle the route /, in other words, just the default web server route, and serve up stream. And then we say log.fatal, which means log everything until a fatal message comes in, and then exit the program of HTTP listen and serve. HTTP.listen and serve starts up a web server, and on whatever host and port we pass in. So when we run this code, if we say MJPEG streamer, and we put in a, what are the parameters? I forgot the parameters, so let's take a look. Oh yeah, camera ID and host port. Okay, so camera ID 1, and if I say host 0.0.0.0, which is anything, and we put it on port 8080, okay, so now it's running. So let's go back to the web browser, except this time, if I go to localhost 8080, there I am, streaming into the web browser using nothing but motion JPEG coming all from OpenCV, all in pure Go, no other moving parts. This saves an enormous amount of hassle and difficulty when trying to do web streaming video. And you could see where you could very easily combine this with the previous example, doing the motion tracking, and you're, a bunch of the way along to your online web-based security system. Hint, hint. All right, so and we see here from our log, the two streams that were connected. We can handle many, many simultaneous streams. I meant to have a tunnel address so that all of you out in our internet studio audience could stream directly to this computer, but I ran out of time. I'm sorry about that. All right, so we'll go back. So the last of the three magical examples is object counting. So object counting is something which is extremely important and pretty difficult to do. There's a lot of different ways to go about it. The way that this particular example is, it combines two techniques. The first one is it uses the mixture of Gaussian to extract, again, the foreground from the background, so we know that we're measuring. And then after that, it uses something that's called image moments. So image moments are basically a way of determining the moment centroid, which is sort of the average point of motion within any given particular image. So if that centroid passes over a line, a red line in the image that we did say, moving past this line indicates that you are to be counted. So let's take a look at the code so we can see how that actually works. Same package main, same imports from the Go standard package line, same GoCV. We don't need anything extra. In this case, though, we do have a couple other arguments. We're going to take our data from an external file of traffic from an overhead overpass that I have. It takes the line, which is the location of which where we want to draw the line, which axis, whether it's the X or the Y axis to use. That way, if it's things that are moving up or down versus things moving left to right or right to left, we can just use the same program. And then the width of the area in which, crossing into this area indicates that we should count you. So we open our video capture file. We open a new window, same as before. This time we have 3 image maps. We have the image that we're bringing in initially from the camera. We have the image that we are extracting, which is just the foreground image. And then we have the cleaned up image that we're going to use for the analysis. And then we declare our friend from before, the background subtractor mog2 to get the foreground image. And then we initialize our count to 0. So the repeating loop is, again, grab the video, put the image in there, run the image, continue if there is not one. So the first stage of cleanup is we're going to mog2.apply so that we get only the foreground image. Then this time we're going to use the GoCV.erode. Last time I think we used dilate. So now I want to look and see. What did we use to clean up that other image? Yeah, last time we used dilate for the cleanup. This time we're going to use erode for the cleanup. These are 2 different filters of the hundreds of different algorithms and filters supported in OpenCV, which is why it's so powerful to use. And then once we've got that cleaned up image, we're going to use the GoCV.moments API. And so moments returns to us a map that has in it the area. And if that area is large enough, then we can calculate the X and Y coordinates of where that moment centroid is located. If we're looking for a Y axis, if it crosses over the line, then we increment the count and we draw the line. If it's the y-axis, then we do the same thing and we draw our line. And then we display our count based on however many we've detected. Could be 0, however many. And then we show that image and loop through again. All right, so let's run our code here. So if we say counter, what are my parameters? Counter, and then my file name. I have cars driving under bridge. I'm going to do it at the 500th line based on the y-axis with a width of 40. And so here we see this freeway overpass, and up here on the top left, you can see the count incrementing as it attempts to determine the cars passing over this line. And one thing about image moments is it's not the most accurate algorithm when confronted with multiple objects, but it is extremely efficient and fast, and so it's able to handle doing many things at one time, and can run on processors that are not quite as powerful potentially. But again, there are other ways to do this. This is just one of them, and it's one that we are helping show to all of you wonderful people out in the internet-verse. So eventually so that's it on that. So that, my dear friends, is GoCV. And you can check out more information at GoCV.io. It is all open source. It is Apache 2.0 license, so you can use it for your commercial as well as your non-commercial endeavors. And with that, I say thank you very much. I am Dead Program, and I am now happy to answer any of your questions. So first question, does GoCV support most of the functionality of OpenCV? The answer is no, not yet. The way that we designed GoCV is to make it, for example, camera calibration. That's next on my list, personal list. So the way that we designed GoCV is to create a one-to-one mapping between the files in GoCV and the modules in OpenCV. That way, when you encounter something that GoCV doesn't support yet, it's easier to, pretty easy to figure out where you need to add it. Or if you're looking for something, you can figure out, whether or not it's been implemented yet. So that's one thing. Another is, one difference between GoCV and some of the other wrappers that have been created for OpenCV, for example, Python. So a lot of people use Python for OpenCV, not because necessarily Python is, the best or worst or anything else, but largely because there's a really great generator built right into OpenCV that creates wrappers for everything automatically for Python. So, and that sounds really great until you look at that code and you realize, it is really complicated, not just OpenCV, but the generative part. So there is Swig wrappers that you can use to try to automatically generate code in various languages. Swig is, you can learn more about it at swig.org, and there is Swig support built into Go. So in theory, one could just automatically generate wrappers for Go right from the C++ code. However, in practice, it does not work very well at all for two reasons. The first is the wrappers that you end up with are not very Go-like. In similar fashion, that's why Python doesn't do that. It generates wrappers that are very Python-esque and make it, very nice to use from Python. So you really want a Go wrapper in the same fashion that, works and makes sense within the way that Go code is supposed to work. The other one, though, is that Swig is really, really hard to work with. Even for people who've worked with it a lot, like I've used it quite a lot myself. So there was another project that has existed for a while as a wrapper around older versions of OpenCV, but when OpenCV switched to C++, they basically got bogged down, and for about a year and a half, nobody was able to make any progress because they couldn't figure out how to use Swig properly from Go with OpenCV. In fact, the same thing happened. I tried it. I spent a long time working on that, and I failed. But then I thought about it, and I realized it's a lot easier to handwrite wrappers than it is to actually develop computer vision algorithms. So started just implementing wrappers manually, and I've gotten through quite a few. We have a lot more work to do, but at some point, in the not too distant future, most of the functionality that you commonly need to access will already be implemented, and then we'll just be filling in the rest of the white spaces. So things like camera calibration, for example, because that's something I need myself. So we have a question here, how do we manage the concurrency in Go? So if we have a concept of threading, and how do we manage that threading? And so in Go, we only deal with Go routines. We don't actually do ourselves anything with threading. So now in C++, we need to be concerned about threads typically, but when we're using CGO, CGO actually does a lot of this work for you in that when it creates the thread from the C thread, from the thread that the Go routine is launched on, it makes sure that that C thread is always associated with the green thread that the thread for the Go routine is being called from. And so, sometimes that may have a negative concurrency implementation compared to a pure Go program, but in practical terms, that's what you actually need to make sure that C++ managed code doesn't, blocks of memory don't move around, disappear without the associated pointers being updated as well. So like the example I showed earlier with the MJPEG streaming, you've got one thread essentially that's handling all of the OpenCV interaction, and then you've got however many threads are being accommodating the web server for the motion JPEG streaming. Just because typically, you would have dozens or hundreds of people who are trying to get their motion JPEG images served up, and then you've got a smaller amount of data being served up from the camera. Or perhaps in a different use case, one that I've done quite a few times, I'm flying a drone where I'm getting the computer vision and it's running, in one thread, and I've got other Go routines that are handling things like my joystick so that I can, fly the drone around, and they're handling communication with the drone so that, it receives all of the updates from the ground control station, in a relatively quick manner, since, this is very important when you're flying objects under computer control. So the question is, a very important question, so how do you actually deal with version control and package management in Go, since, people who have been using Go have learned relatively quickly that the way that Go, the language itself, handles package management and versioning is essentially it doesn't handle it at all. It's, you can do whatever you want, which has proven to be quite tricky. Do whatever you want means either do nothing and, things suddenly break because, one day someone updates some code and next thing you know, your code doesn't work anymore. So, that's obviously not a scalable development process. And so fortunately, this is a realization that the Go community has come to, and there's a project called DEP, which is not yet an official package management tool for Go, but it's sort of the unofficial official one. It's actually in the Google organization and GitHub, and it's really the result of a consensus as far as the community itself, not just technological, but sort of how should we do package management. So if you use semantic versioning and you tag your Go packages and you are using DEP, then you can basically step up to the latest state-of-the-art for Go package management and versioning. And even though it's not, quote unquote production ready according to its own website, I know many, many companies that are running it production right now. So according to Microsoft, that's one of the contributors, it's ready for production. So ship it. There are AI frameworks for Go. So, yeah, actually, one of my there's a few things going on in the machine learning space in Go. So my own personal thing that I'm working on currently right now is right within OpenCV itself, there is the ability to load, there's a whole machine learning section for doing the image classification. That way, you can plug it all right into, you can combine, traditional computer vision along with, other techniques. So right within the OpenCV itself, you can actually load Caffe models, you can load TensorFlow models, and another one that I'm not as familiar with and can't remember right now offhand. So one of the next extensions that I'm going to be adding to GoCV is basically being able to load, a model and then use that for classification. So, first you use your Cascade Classifier to find the face, and then you use, for example, your Caffe model to determine, the sentiment of the face or gender or something else of that sort. So, I think that that's a very good way to combine the, sort of a hybrid model of using algorithmic along with, network. There's also several different neural network plugins for, a couple of different neural network plugins for OpenCV as well. TinyDNN, which is, very small, very fast, very open source. There's also some plugins for some of the more proprietary ones, but I've been sort of, I'm very open source focused, so that is, so that. But one interesting thing is that once I've gotten my first go round of implementation for what I just mentioned for the machine learning and for neural networks, then I'm very interested in combining that with some of the code that's in the Intel computer vision SDK, not part of the photography vision library, but part of some of the neural network and hardware accelerated stuff. But so that'll be coming, possibly by the end of the year, very likely, if I get time to work on it. Yeah, TensorFlow has support for Go, exactly. So I mean, a good way to look at this is, there's a lot of tooling that's out there in Python for training, but Python's not really where you want to deploy your code to production, especially with, Go is much superior for deployment just because it builds, you can build a single executable file with no external dependencies that's statically linked. And, that's a great way to deploy software. So, use Python and the tooling to, TensorBoard or whatever to, train your networks, train your models. And then once you've got things, nice, then you're like, okay, cool, let's deploy the production, and the TensorFlow support for Go is basically using Go to execute them. And I think that's a great way to look at it is, who said you could only use one programming language for everything? Did I say that earlier? I said maybe you should, but, So yeah, the question is, can we combine Go and the Intel Mobius? Definitely, I'm sure that's going to be possible. You can call the C++ code, you can do it from Go. I need to spend a little more time on figuring out how that will work, myself. But I think that by just plugging it into GoCV in the same fashion, then it'd be really neat to be able to use a neural network for classification, again, plugged into your computer vision stuff. The ultimate power, hardware acceleration. And let's see, Docker. Yeah, totally can be done within Docker. So I think the question is sort of, what about doing some sort of distributed computing with GoCV? I'm not sure if that might be sort of an orthogonal concern to what GoCV itself does, as far as, if you get the data from GoCV, then, if you wanted to do some type of distributed processing as far as, classification or distributed training set or something like that. Yes, Alexis, that exactly, or the answer to this question. Thank you. Thank you for, yeah, well, as far as providing a sample, yeah, that'd be really cool to have a sample that did that. In fact, if anybody wants to work on something like that, I would love to help support. I think it'd be really neat to do. There's a few different ideas that pop into mind. One is a distributed multi-camera running in different, each camera is in a different container, possibly running on different devices, for creating sort of like what Intel does for the NFL and for World Cup soccer, with the really awesome 360-degree views from other cameras. I'd love to do that, except do it in open source ourselves. That'd be really awesome. There's a bunch of cool applications. Distributed processing ones where it's, getting visual data and then doing a cluster, a training cluster. That way you can, run your own classification trainers and then take that and feedback loop it back in so that you now have new models trained. That would be totally cool. And there's a bunch of applications for the data generated by this that, even though they're not necessarily direct concerns of OpenCV or GoCV, well, I mean, neither is MJPEG streaming. That didn't stop us. That's just a typical thing people want to do. So, as people have more visual data and want more sophisticated use of it, or combining it with other data, you've got SLAM data coming from, or for that matter, implementing SLAM algorithms using these tools. Love to see those sort of things happen. That'd be great. I really saw the camera calibration one. I'm on it. I've got some cameras I need to do that to, specifically because they're fisheye lenses. Exactly. Jinx. Exactly. Yes. They're small, they're really cool, and they need to be calibrated to something sane looking for humans and for my other tracking algorithms. Thanks, everybody. Really appreciate it. And I'll be seeing you. Bye, everyone.